In this video, we're going to be talking about substitution, sometimes called u-substitution, which is an integration technique meant to undo the chain rule. So we're trying to sort of take antiderivatives, right? Integration involves anti-differentiating functions. And so what we want to do is try to think about how to take antiderivatives for composite functions. So, let's just look at a quick example here. We know if we want to take the derivative of something like tangent of x squared, that's a chain rule problem, right? So we take the derivative of tangent and get secant squared. We leave this x squared alone. You leave the inside alone at first. Then you multiply by the derivative of the inside function, so in this case 2x. So reversing this, if we wanted to take the antiderivative, right, if we want to integrate 2x secant squared x squared, we ought to get tangent squared, right? Because these two, and of course plus our integration constant here, because these two things basically say the same thing, right? Like, we're used to thinking of taking derivatives, but we're trying to now sort of think about how to take something complex inside of an integral and distill the original function out of it, which is a little tricky. And in general, integration is harder than differentiation. We have to sort of develop a lot of techniques, and substitution is our first primary technique. It's sort of like the biggest tool in our toolbox. So let's just see the theorem. This theorem basically just says if you have a function whose derivative is little f, right, if you have little f as a composite function, and then you're multiplying by the derivative of that inside function, right, so like in this case up here, little f is secant squared and capital F is tangent, right, and then u is x squared, this inside piece is u. Then basically you can sort of distill these pieces back into the original composite function. So that's kind of hard to track, so let's just do a couple of examples here. So say we want to evaluate something like this. Now, you may or may not immediately observe the sort of derivative relationship here, but we're going to give you some structure for thinking about how to do these problems. So the first thing we want to do is try to identify a candidate for u, where u is the sort of inside function. So if you go back up and look at this theorem statement, u is the inside of the composite function, right? And it's the inside of the composite function here. So we want to try to identify what that is for this particular problem. So we'll talk at the very end about some guidelines for choosing u. But in general, if you see a composite piece, taking the inside of a composite piece is a good bet. So here I've got 2x cubed plus 1 raised to the fifth. So maybe 2x cubed plus 1 is my composite function, like the sort of inside of my composite function. So the idea here is that we're going to replace all our x's with this new variable u, which is a function of x. But you also have to keep in mind that you're not just replacing these x's, but you also have to replace the differential. So when you go to take the differential, well, we know that the derivative, right, of u with respect to x, if we use Leibniz notation, right, that just means take the derivative of this. So that would be 6x squared. So then if we want to rewrite this, right, then we can get that du is equal to 6x squared dx, right? And in general, we can always, we'll just shortcut to this from now on directly from here. So if you take the derivative of this, that means take the derivative and slap the differential on. So if we take our original function, we're trying to take 6x squared times 2x cubed plus 1 to the fifth dx. Well, we can replace this with the 6x squared and the dx. That's all just going to get captured by du. And then 2x cubed plus 1 to the fifth, that's really just u to the fifth. So in switching our variable from x to u, we've replaced this sort of complex looking thing with this much more straightforward looking thing. So now we're going to integrate just using standard power rule. So this is 1/6 u to the sixth plus c. But of course, we didn't actually want our answer in terms of u. We wanted it in terms of x. So as a final step, you have to go back and say, oh, well, what was u? So in this case, it's 1/6 2x cubed plus 1 to the sixth plus c. And you can check that if you take the derivative of this, this is what you will get, right? You'll take down the 6 to take the derivative, which will cancel that 1/6. You'll then have 2x cubed plus 1 to the fifth, but then you'll have to multiply by the derivative of the inside function, which would give you that 6x squared, and of course your c would disappear when you're taking the derivative. So this sort of like structuring of u and then replacing, right, your old function with your new function is where a lot of the work comes in u-substitution. Sometimes it's not immediately obvious what the choice for u should be. But let's go ahead and do another one or two here. So now let's say you want to evaluate the integral of tangent. So tangent theta d theta. This is not one of our standard trig identities for anti-differentiation. So this doesn't immediately look like it has a composite function, right? So sometimes you have to do some rewriting before you can see what u should be. And so you might pause and ask yourself, what's a standard way to rewrite trig functions? So in general, writing trig functions in terms of sines and cosines is usually good because every trig function can be written in terms of sines and cosines. So here we can recognize that this is sine over cosine. And again, there's no composite functions here, but we do have now, at least there are multiple pieces to this. And so our other guideline for choosing u, in our first example, we mentioned that a guideline is trying to take the sort of inside of a composite function as a good guideline for u. But another good guideline for u is to take things in the denominator. So in this case, say we let u be cosine, then sort of shortcutting our differential, I should take the derivative of this, which would give me negative sine theta d theta, right? And then I don't have a negative here, so really, like, if I want to replace, I'm not replacing negative sine theta d theta, I really want a positive sine theta d theta, because I can imagine this as looking like this, right, if I sort of just peel this fraction apart. So all of this is going to sort of be replaced by my differential, and if I isolate this for what I want, right, I don't actually want a negative sign, so I can divide both of these by a negative sign. So I can see that if I want to replace this, I'm going to do that with negative du. So 1 over cosine, that's 1 over u. And then sine theta d theta, that's negative du. So then I can factor out that negative, and I have just 1 over u du. So if you go back and look at your antiderivative table or just know what this happens to be, you may want to pause and ask yourself what this is. This is negative natural log of absolute value of u plus c. And then you can do a little bit of rewriting with this, and we definitely have to go back and substitute. So this is negative natural log absolute value of cosine theta plus c. But really we can take that negative in as an exponent. So a lot of times you'll see the antiderivative for tangent written slightly differently. So if this is cosine to the negative first, that's 1 over cosine, which is the same as secant. So often you see this written as natural log of secant. So if you want to find the antiderivative for tangent, it's natural log of the absolute value of secant plus c based on this sort of undoing of a composite function. And you could try this. Take the derivative of this and see what happens, and what you'll do is get tangent. Okay, so this is another example where you might use u-substitution. So let's just do one more, and then we'll call it a day. So you may want to pause and ask yourself, what's the right choice of u in this function, based on our two guidelines from before. So in this situation, we do have a composite piece, right? We've got 2 to the x plus 5 all being cubed, but we also have a denominator. So in this case, we're going to apply both rules and make the inside of the composite piece in the denominator our u-substitution, right? So if we do that, that's going to make du the differential 2 to the x natural log of 2, because that's the derivative of all of this, and then of course times dx. And it turns out that that's exactly what we want here, right? Because if I take this expression, again, I can sort of like peel this fraction off. And then I see that this is really like 2x natural log of 2 dx. So I want to replace all of this, which is great, because du is going to cover all of these pieces. So then this ends up being 1 over u cubed times du, right? Because all of this is du, and then this is 1 over u cubed. And then this is relatively easy, right? I mean, this is just power rule. This is u to the negative 3 So then if I do power rule here, I should get 1 over negative 2 u to the negative 2 plus c. So then with a little bit of rewriting, right, I get negative 1 over 2 times 2x plus 5 squared plus c. Right, because a negative 2 exponent, I can make that a positive 2 exponent in the denominator, and I'm also substituting back in for my variable u. So this is the basics of u-substitution. We'll have another video that describes some sort of trickier situations with u-substitution and addresses what happens with definite integrals. So you might have noticed that we only did indefinite integrals this time, but essentially the same principles work for definite integrals as well. And just so that you have them written up, right, the guidelines for choosing u are you want the insides of composite functions. So like for instance, if you had this in here, you might try u is 5x squared plus 1. Or in this case, you might try u equals 3x to the 4th. Or in this case, you might try u equals 5x plus 3, right? The inside piece for all these composite functions. That's a good thing to try out and see if you can sort of rewrite using this type of substitution, and things in denominators, right? The whole denominator or just maybe the part of one, like for instance in our last example when we had a composite thing in the denominator. But this is the basics of u-substitution, and substitution is the primary rule or technique in taking antiderivatives or for basic integration.